Hey everybody, today we're going to be talking about different kinds of chemical bonds. A chemical bond is when you have two atoms that are either going to share electrons between the two atoms, or the electrons are going to be transferred from one atom to another atom. So if you look at this page here, you can see these two kids over here are very nicely sharing. So they would be a certain type of bond in which the electrons are shared between two different atoms. You can see over here, not quite the same situation. We have a little girl, and she is not doing a very good job of sharing her tricycle. She is literally taking it away from this other little kid. So depending on whether it's a sharing or a transfer determines the type of bond. So we have two types of bonds. We have ionic bonds, and that's this one up here. This is the not sharing. The electrons are going to be transferred from one atom to another atom. And then we have this situation down here, and this represents a covalent bond. Covalent bond is where the electrons are nicely shared between the two atoms. So let's talk about ionic bonds first. So the ionic bonds, again, are going to transfer an electron. Now, the reason they want to do this is because of the octet rule. Remember, we like to have a full valence shell. And so let's look at sodium, for example. This is sodium right here, and it has 1, 2, 3 shells to take all of the electrons that it has. But it doesn't like this outer shell out there. It doesn't like it because it only has 1 electron in it. And again, we want 8 in that third shell. And so it's easier to get rid of an electron than to try and get 7 more to fill up that outer shell. So it's going to donate an electron away. When it's given an electron away, again, it's going to become a positively charged ion or a cation, right? But you can't just throw an electron out with the trash. It has to be picked up by another atom. And so it's going to be picked up by an atom that wants to fulfill its octet rule. And so something like chloride is going to pick it up because chloride has 7 valence electrons. It only has 7 in the outer shell, and it really, really wants 8. So sodium's electron gets donated, and it gets accepted by chloride. When chloride accepts the electron, it becomes more negatively charged because it's accepted something that's negatively charged. Remember, electrons have a negative charge. And so you end up with a cation, sodium, and an anion, chloride, and they're attracted to one another. So an ionic bond is one in which the electrons are transferred. It forms an anion and a cation, and those two are attracted to one another. So ionic bonds were about transferring electrons, but covalent bonds are about sharing of electrons. You can see here these two kids are each sharing the earbuds and listening to music together. And in this diagram, you can see 2 atoms of oxygen that are joined together, and they are sharing the electrons. One molecule of, or one atom of oxygen isn't stealing away the electron from another atom of oxygen. What's shown here, you can actually count the electrons. 1, 2, 3, 4. I'm sorry, my pointer's not very good. You can see that they are actually sharing 2 pairs. Remember, a pair is 2. If there were only 2 electrons shared between these, that would be a single bond. But here we've got 2 pairs shared, so that's called a double covalent bond. Now there's 2 types of covalent bonds. Both of them involve sharing of electrons. One of them involves unequal sharing. We're going to talk about that in a minute, but first I want to talk about what polar means. So think about the planet. On one top side of the planet, we've got the North Pole, and on the bottom of the planet, we have the South Pole. South Pole has penguins. North Pole has polar bears. When you talk about polar opposites, usually you're talking about 2 things that are as different as they can be. as far away as they can be from each other. And in fact, if you think about the North Pole and the South Pole, they're about as far away as you can get from each other on Earth. When we talk about covalent bonds, we have two types. One is a polar bond, and remember, polar means different. A non-polar bond would be the opposite. It would be the same. So remember how I showed you that picture of these two kids, and they're equally sharing the earbuds. That's great. They're being very nice to each other. There's no difference between how much music each of them is hearing. However, if you look at up here at this picture, so I have kids. I can imagine what's going on in this picture. This kid, the little boy, is holding the ice cream, and he's saying, yes, I will share my ice cream with you. But I can imagine he's probably doing 1, 2, 3 licks for me and 1 lick for you. 3 licks for me, 1 lick for you. So even though he's sharing, it's what we call an unequal sharing. And the reason this happens is when there's a bond between two atoms where the electrons are shared, but they're unequally shared. One of the atoms pulls and attracts the electrons much more strongly than the other atom. So the electrons spend more of their time over near one atom, we'll call him Atom, than over here on the other atom. So there's an unequal sharing, and that's why we call it polar, because there's a difference. There's a difference in the strength of the attraction of the electrons. In a nonpolar, everybody's happy, everybody's equally sharing. Now these are both covalent bonds. But underneath covalent bonds, there's two different types of covalent bonds. So let's look at this in more chemistry type drawings. You can see here, this is the nonpolar example, and you can see that you have oxygen atom and another oxygen atom, and they're forming oxygen gas. So there's 2 oxygens here, and they are sharing these 4 electrons. So this would be a double bond between them. There's no difference from this side to that side of the molecule. That's nonpolar. Sharing electrons, not different, not polar. Up here, however, you have polar example. You have an oxygen, and it's sharing electrons with 1, 2 hydrogens, but you can see that there's a difference. This side of the molecule is very different than this side of the molecule. The electrons are actually much more attracted to oxygen than they are to hydrogen. So they spend much more of their time over here and much less of their time around this hydrogen atom or that hydrogen atom. So this shows it a little bit more in detail. What happens is because the electrons are spending more of their time orbiting around the oxygen atom, it's going to make this end of the atom slightly negatively charged. Remember, electrons are negatively charged. So if they're hanging out over here in this crowd, this part of the molecule is going to be a little bit negative. And again, if we've got electrons that circle our hydrogen ions, but really don't spend a lot of time over here, they keep on sort of looking over with the popular kids over here on the oxygen, it's going to be not so negative over here. It's actually going to be slightly positively charged because, again, these electrons are more attracted to oxygen than they are to hydrogen. Okay, so you end up with something where there's unequal sharing. The oxygen is getting more attention from the electrons than the hydrogens are, and it ends up with a weakly negative end and a weakly positive end. So this would be a polar molecule. There's polar bonds holding the atoms together, and the 2 ends of the molecule are slightly different. Remember, different is polar. Okay, so why do we care so much about molecules being polar or not polar? Well, because when you have a molecule that has polar covalent bonds in it, we end up with this slight negative and slight positive end on the molecules. And what happens, remember, something that's slightly negative is going to actually be attracted to something that is slightly positive. Now, they're not going to form an ionic bond. It's not that much of an attraction because there isn't that much of a charge. It's just a sort of transient attraction. So for example, the hydrogen on this molecule is going to be slightly positively charged, and it's going to be just attracted a little bit to the negative charge on this oxygen. It's a transient attraction, kind of a how you doing kind of attraction. Not a covalent bond. Remember, covalent bond is a very strong bond. That's like a marriage bond. It would be more like just checking out the person walking by on the street. So this causes a cohesion between, for example, water molecules that enables a lot of different biological processes to happen. So remember, we've got covalent bonds that are polar within each of the water molecules, and we've got a hydrogen bond, which is a slight attraction between the positively charged end of one molecule and the negatively charged end of another molecule. There's a lot of important things that hydrogen bonding does. When you look at your DNA, we know that DNA is in a ladder shape, and we know we have bases in between. What we might not know is that what holds those bases together are hydrogen bonds. They're very, very weak bonds, transient attractions. But when you have hundreds and hundreds and thousands and millions of them, that's actually what holds the two sides of the DNA ladder together. Also, in protein, if you have a large polypeptide that you want to fold up into a protein, one of the things that actually helps that protein fold into the proper shape are hydrogen bonds. The other important thing that water does for us, or that the polar covalent bonds that allow water to function does for us, is that it causes water to be an excellent solvent. Remember how we talked about an ionic bond, and you might have a sodium and a chloride, and they're going to come together in an ionic bond because they're attracted to each other. The cation is attracted to the anion. Well, the reason why NaCl, or salt, dissolves in water is because all of those water molecules are going to come in and they're going to disrupt this attraction. They're going to disrupt this bond between sodium and chloride. And the way they do it is that the negatively charged end, the oxygen end of all of the water molecules, is going to be attracted to the sodium. And the positively charged end, the hydrogen end, is going to be attracted to the anion, the chloride ion. And it's going to disrupt the bond between these two. So if you ever put salt in water and stir it around, you'll notice that it no longer makes salt. And the reason for that is because the water is an excellent solvent. It disrupts ionic bonds. So any salt that you put into water is going to be disrupted. That's it for today.